Howdy, howdy, howdy. We're talking light and optics still. We're in topic 7, and we're going to start talking about energy and wavelength. So we've seen this diagram a few times already, and really what it's showing are the different wavelengths of the different parts of our visible color spectrum. And you'll notice that when we see red, it's because we're seeing a certain wavelength. This wavelength allows us to see red. If we shorten that wavelength a bit, it becomes orange. We keep shortening it, it becomes different colors. Let's say we get all the way down to violet and we continue to shorten it. Well, eventually what will happen is that, number one, it will become invisible to us. We'll see here on the entire spectrum here, shorter wavelength than violet turns into ultraviolet. And ultraviolet is invisible to our eyes. And P.S., that's why they also call it ultraviolet, right? It's more violet than violet. It's ultraviolet. And yet it doesn't look purple or the color violet. And that's because it's invisible to the human eye. If we were to continue shortening those wavelengths, we would eventually turn into X-rays. And if we continue shortening those, we eventually become gamma rays. Okay. But anyway, I'm getting ahead of myself. What do we know about light? Well, we know the first basic principle of light is that it is energy. Light is a form of energy. And we also know that light consists of waves that travel in straight lines. And those straight lines do bounce when they reflect. They do bend when they refract, but they are working in straight lines. Our essential questions that we will be able to answer at the end of this topic: how can we show that light behaves like a wave? How can we measure wavelength and frequency? What is the relationship between wavelength and frequency? And lastly, what's the relationship between wavelength and energy? So take a look at this, and I'm sure this is something we've all experienced, typically in the morning or the evening. Sun is setting or rising. This is beautiful golden light, and yet notice the curtain here. It looks like that light is spilling past the curtain, which doesn't really make sense. The curtain should be blocking out the light. Why does it look like the light is kind of skipping around it or going past it? Didn't you just say that light travels in straight lines, Lewis? What the heck is going on here? Well, remember, yeah, that's where it's happening. Well, remember that not only does light travel in straight lines, light is energy, which means it's going to be traveling in waves. So I wanted you to pause this video, and I want you to watch this video, the entire thing, and then come back. So go ahead. And you're back. That's awesome. I hope you enjoyed that video. This is one I quite like. I feel like Buddy explains himself quite well and does a lot of really good jobs showing how energy travels in waves, and more importantly, how those waves are able to interfere with each other and bounce off one another. So anyhow, how does this apply to what we saw in the last slide here? Well, the light that's coming from the sun here, yes, it's traveling in straight lines, but you have to keep in mind that those lines are waves. So those waves are kind of coming around the curtain, and that's why it looks like it's spilling across a little bit, because in a way, it is. Those rays of light, the waves are kind of going around the curtain, and that's why it looks like there's light coming from the curtain itself right there. And if we look back at some of these waves, that might make sense. Imagine the curtain's right here. The wave is kind of going around it a little bit. Okay, moving forward. So again, guys, this is something you're going to hear a lot. This lecture is that light is energy and it travels in waves. So that experiment in that last video that you guys watched, it's called the double slit experiment, as he told us. Okay, and it provides evidence that light, in fact, does travel in waves. Okay, and just like in a water experiment like this one right here, we can see how those waves are interfering with each other. If you've ever gone tubing behind a boat, say like on Gull Lake or somewhere, you'll know that when the boat goes around in circles and makes donuts, those waves add together, making massive waves. And if you're the one in the tube, you know what happens. You get launched really, really high. It's pretty fun, actually. Okay. And light behaves pretty darn similarly. We can see a model representing that over here. We can see these light waves, they're traveling, they're white light, and then they have to squeeze through these tiny little narrow slits. And we can see how it's not white light anymore, how the light is being broken up into different parts. Thanks to the different wavelengths of those parts, we can see how the light is combining in certain areas as well, just like they would with water. Okay. And because the light behaves this way, we know that light travels in waves. This is evidence. It's not just us saying, hey, we think it travels in waves. We know it travels in waves based on this evidence. And again, light, waves, straight lines. Yes, we get it, Lewis. All right, let's talk some vocabulary. So we can take a look at a wave in a diagram here. Okay, now notice there's a midline. It splits it right in half so that it's symmetrical. Okay, we'll say from the midline to the very top of the wave, we would call that amplitude. Notice the amplitude on top of the midline is the same as the amplitude on the bottom. That's how we know that that's the midline. Okay, parts of a wave, well, the top of a wave, we call that the crest, and the bottom of a wave, we call that the trough. Okay, when you measure from trough to trough, or from crest to crest, we would say that's the wavelength. Okay. Now, not on this slide here is something called frequency. Frequency is how often the waves are occurring within a stretch of time. Okay, so we would say this wave has a pretty high frequency because it's going up and down, up and down, up and down pretty darn quick. If we go all the way back to this slide here, we can see that violet's frequency is a lot quicker than red's frequency. And conversely, we can see that the wavelength of red is very long and the wavelength of violet is very short. So we can say that the relationship between wavelength and frequency is that the longer your wavelength, the shorter, or the smaller your frequency. The shorter your wavelength, the faster your frequency. One way you can think of it is this. I've got stubby little legs, they're not very long. When I try and sprint, it looks like my little legs are going really fast. Kind of like a short wavelength. If you look at someone who has long legs, it looks like they're running, doesn't look like they're running slowly, but looks like their feet aren't moving as fast because they aren't. They don't need to. They're traveling more distance because they have a longer running stride, kind of like a long wavelength. Long wavelength has a smaller frequency. Excuse me. Moving on. And again, to measure wavelength, you go from crest to crest or from trough to trough. Scientists use nanometers to measure these. Nano means 1/1,000,000th, I believe. I just Googled it to be safe. Nanometers means 1/1000,000th of a meter. So that's pretty darn small. Holy smokes. Taking a meter and you're cutting up into 1,000,000,000 parts. And one of those parts is a nanometer. And again, to measure frequency, you count the number of cycles within a certain amount of time. So how often is it going up per second? And we measure that in hertz. The most common place where we've all seen this is the radio selector inside your car. So when you go from 98.9 to 100.3 to 98.1, what you're changing is what your radio is trying to pick up, what radio frequency your radio is trying to pick up. So it's trying to get 98.1 hertz or 100.3 hertz. And it's just relaying what the different radio wave types are signaling. Okay, another graphic showing the different wavelengths for the different colors within our visible color spectrum. Notice violet, faster frequency, shorter wavelength, and down towards the reds, longer wavelength, smaller frequency. Another one. And take a look at this, guys. They've even got it measured out for us. So for us to see violet, that we need wavelengths that are traveling or that are 400 nanometers long. If somehow we took this wave and we stretched it out, it would eventually turn indigo, and if we kept stretching, turn into blue, into green, into yellow. And again, to go back to topic 6, we're able to distinguish these colors thanks to the cones that are inside our retina. These cones take in these different wavelengths of light and interpret them for us. This is a website you may have already used. Depends if you're checking out our classroom assignments or not. If you haven't seen this one yet, definitely click on this link and check it out. This is a great video. You need to watch it on your own time. Again, just showing how longer the wavelengths get to this side, right? And as we travel further to the right, wavelengths are getting shorter to the point where we reach red. Now we can actually start seeing some of this energy. If we get smaller than purple, or rather not purple, violet, if we get smaller than violet, we become ultraviolet, X-rays, gamma rays. This video, watch it until 3 minutes and 20 seconds. And while you're watching it, I want you to think of these 3 questions. What is the difference between visible and invisible light? What is the relationship between wavelength and energy? And when you increase the energy of something, what happens to its wavelength? Parameter Lewis, my goodness. Sorry about that. Okay, so watch that video. Cool. And here's some of your answers here, guys. And remember, what is the difference between visible and invisible light? Well, obviously, one you can see and the other one you can't. But more importantly, and what you need to know, the difference is wavelength. If it's shorter than violet, we can't see it. If it's longer than red, we can't see it. It comes down to wavelength. What is the relationship between wavelength and energy? Well, the shorter your wavelength, the higher your energy. And if you increase the energy of something, what happens to its wavelength? The wavelength gets shorter. Shorter wavelength, higher energy. Now, we know that the sun gives us off white light. And when we're down here on Earth, the sun typically looks kind of yellow. If we were up in outer space and we weren't surrounded by an atmosphere, the light coming from the sun would actually look white. It wouldn't look very yellow to us. It would look more pure white. But because we're surrounded by this atmosphere, the light refracts and it will look different colors at different times of day. Take a look at Buddy right here. He's a little bit further around the Earth than this guy, okay? And that light, as it's traveling at this angle, the yellow and blue portions are being absorbed, while the red is allowed to just continue traveling, okay? That's why in the evenings or in the mornings, we have those beautiful purples and violets and reds and oranges. And this is basically because different wavelengths of light are being absorbed. Some are able to continue passing through. Lasers are pretty darn cool. And what they do is they take advantage of wavelength. When we have an ordinary light, typically it's white light. And we can see all these different wavelengths, and it's kind of like a big mess. They're all tied up and bouncing off each other, and they're around each other. And it's incoherent, okay? But when we have a laser, it's not only the same wavelength of light, but those wavelengths themselves are perfectly organized, kind of like knitting on a sweatshirt, okay? They're perfectly organized and focused. And that's really the difference between laser and regular light, is that laser light is coherent. It's organized. Take a look here. We've got regular light, a whole bunch of wavelength, kind of chaotic. Here we have just red light, okay, but it's not a laser yet. because these wavelengths aren't organized. They're not coherent. Here we have laser light. Look at how these wavelengths are perfectly meshed together in focus. Same again. Regular white light, different wavelengths. Just one type of color light, but again, the wavelengths aren't synchronized or fit together. And here's our laser. Look at how they're perfectly matched up and focused. And look at this little fella. He's pretty excited about it. And there it is, guys. That is topic 7. I hope you guys were able to fill out all your notes on your follow-along notes. And if you didn't, feel free to pause or rewind and go back and get those done. All right, guys. I wish you a good rest of your day. Bye for now.